Hi Calc2 class. In this video we are still working on the section 11.3, which is the integral test, and in the last video I had just proved that this was true, and I used the integral test to show that this thing that's called a p-series, which is just 1 over n to the p, that series converges if your p is greater than 1 and it diverges otherwise. I want to get a little bit more practice with the integral test, so I'm going to show you another example. And there's more than one way to do the one that I'm showing here, that sum of square root of n plus 4 all over n squared. So I'm going to mark it method 1 and method 2, but the first method I'm going to do is the integral test because we're practicing that right now. Okay, so remind you what the integral test says. If you make up a function whose heights agree with the terms in the series, and that function is positive, continuous, and decreasing for x greater than or equal to 1, then the integral converges if and only if the series converges. So you can decide the convergence of the series based on the convergence of the integral. This is one of your more intuitive convergence theorems. It's totally believable if you think about it. Because what you're doing is you're just taking a continuous curve and you're approximating it with rectangles. And it's pretty believable that if the area under the curve is infinite, then the rectangles that you're approximating the curve with will also be infinite. And on the other hand, if the area under the curve is finite, then it's not that unusual to expect that the area under the curve that's being I should say the area under the rectangles that is approximating the curve will also be finite. So this theorem is pretty intuitive. All right, but we're going to practice it again. So this one we're going to do the integral test. The function you make up is easy to decide. It's just going to have the same expression as the terms in the series. So in this case, that would be square root of x plus 4 all over x squared. All right, so the top's positive no matter what. So is the bottom. You can't stick 0 in, though, because that would make the bottom 0 and it wouldn't be defined. And you can't stick negative numbers into that square root, so you have to stay above 0. So the first thing we're going to notice is that the function is positive for x greater than 0. And there are theorems that'll say back in Calc 1 that the quotient of two continuous functions is a continuous function, except for the bottom is 0. So we'd have to stay away from that. And then it's not defined at negative values here, but root functions are continuous on their domains. So you don't have to state any theorems. You do need to tell me where your function is continuous. This one is continuous for x greater than 0. Can't be 0 because it makes the bottom 0. Can't be negative because it makes that square root undefined. So that leaves the decreasing part, and we're going to take this all together as opposed to separating it. Well, no, let's separate the terms because that'll make it easier to analyze. Well, let's separate the terms before we take the derivative. You could say that's the square root of x over x squared plus 4 over x squared. This is x to the 1/2, and then this is x to the 2, but if you move that to the top, it'll be subtract 2 from the power, so that'll be x to the minus 3 halves, and this one will be x to the minus 2. If you do that, then it's just power over when you take the derivative. The reason you want to take the derivative is, if you remember from Calc 1, wherever a function has a negative derivative, that's where you're decreasing, and we're trying to find out where it's decreasing. All right, so its derivative is minus 3 halves x to the minus 5 halves, and a minus 8x to the minus 3 if you take a derivative. And then you could factor a minus sign out, move those things with positive powers to the bottom. Well, I should say move to the bottom and make positive powers, because then it's easier to analyze. So that's the derivative. Now you can't plug in 0 because it's undefined. You can't plug in negative numbers, so it's undefined. So you're already only talking about the values that are above 0. And if the values are above 0, then this is positive and this is positive. And then the negative of two positive things added together, that's going to be negative. So that's going to be less than 0 if x is bigger than 0. And that means f is decreasing on 0 to infinity. Okay, so that's the third thing. It's positive, continuous, and decreasing for 0 to infinity. And if you're that on a larger set, then you're also that on a smaller set. So you can say that you do meet this condition, that f is positive, continuous, and decreasing for x bigger than or equal to 1, because that set is part of this set. That means you can apply the integral test. You do have to verify that you have met the conditions for theorems that you apply, including the integral test. So this is a necessary part of the solution if you solve a problem. Okay, now we'll go ahead and do the integral. It's improper, so you have to do a limit to calculate it. Just let the upper limit go to infinity. And then to do the antiderivative, we will first write it in the way you did it before, the negative powers, because then you just have to make the power one bigger for the product rule, and then put the right coefficient in front of it. So this would be x to the minus 1/2, and then a minus 2 out in front. So when you take a derivative, it'll give you a 1 for the multiplication. This one would be a minus 4x to the minus 1. So when you take the derivative, you'll get the right coefficient of a positive 4. And then that goes from 1 to t. All right. I'm going to move the things with negative powers down to the bottom. So that would be a minus 2 over t to the positive 1/2. And this one to a minus 4 over t. And then the minus of the minus will give you a plus 2 and a plus 4. All right, so this is infinity to a positive power, so that's still infinity. So this is going to be like a minus 2 over infinity. This will be a minus 4 over infinity and a plus 6. So that's a minus 0, a minus 0, and a plus 6, or just a 6. We don't really care that it's 6. What we care about is that it's finite. So that means the integral converges. And according to the integral test, because the integral converges, the series converges. By the integral test. Okay, so I said let's do two methods. I wanted to practice the integral test, so we did integral test as the first method. So let's do it again now. So this is going to be method 2. All right, it's not geometric, it's not telescoping. I've already done it by the integral test. The only other thing we know really is, at this point, is the p-series for series that converges. So we'll just separate it into two different sums. Okay, this is n to the 1/2, that's n to the 3/2. So if you put it together, that's the same as 1 over n to the 3/2 in the bottom. This one is a plus 4 times the sum of n equal 1 to infinity of 1 over n squared. So I really don't have to do a test. I can just use this fact. Both of these are p-series. Both with a p that's bigger than 1. Here the p is the 3/2, and here the p is 2. But either way, those are both bigger than 1, so both series converge. Since they are p-series. That sum is the same as the original series, so that would be another way to work the problem. There's one more thing to talk about before we finish this section, and that is the integral test is a little bit more versatile than the way it's stated. And this will be helpful in some of the homework problems. The integral test asks for these conditions. It's going to be positive for x greater than or equal to 1. It has to be continuous for x bigger than or equal to 1, and it has to be decreasing for x bigger than or equal to 1. So if you do all those things, then you can apply it. But it turns out that sometimes functions are not decreasing from 1 and up, but they are decreasing from some other integer and up, and that's really all that matters. So you can replace this one if you want as for x greater than or equal to k, where k is any integer. And it's still true. And you don't have to prove it. You can use that whenever it's more helpful than using it with the number 1. You can use it with 2 or 3 or 5, whatever you want. That makes your series work out, because it's true for actually any integer. Okay, so that's it for 11.3, and I will see you in the next video. Thank you.